we began to talk about electrodynamics. And the biggest difference between our previous topics and this topic is, in this case, we have electric fields and magnetic fields changing as a function of time. Okay, so that's what we mean by dynamics. Okay, so electrodynamics. And then in this case, long story short, changing time-varying magnetic field induces electric field, and then time-varying electric field induces magnetic field, right? So that's the most important message that you want to understand. So we began with defining electromotive force. Electromotive force, again, is not force actually. It's rather a potential difference. So, or like a voltage. So you basically tells you how much of a voltage that your current, your electric source can provide. And what Faraday figured out was that actually this electromotive force is determined by d psi dt, and psi here is magnetic flux, B times A or B times S, B times the surface area. Okay, and then from this formula, we deduce that actually dB dt, so time-varying magnetic field, creates electric fields in curly way. Okay, so the Faraday's law in integral form is actually equivalent to Faraday's law in differential form, like curl of E is minus dB dt. And then we start working on just finding this electromotive force in various cases. So we first talked about a moving loop with respect to a current carrying infinite line current, and we also have dealt with this rotating circuit within a constant B field, and we also talked about this case where you have time-varying B field and also moving circuit. So all these cases, you are able to obtain magnetic flux first, and then by taking the time derivative of it, you get the electromotive force, and that's pretty easy thing. And then I also emphasize that after you get the solution, always check whether the direction of your solution is correct by applying Lenz's law. And Lenz's law says that nature basically hates the change. So by using this rule, you can guess in which direction your electromotive force is going to be generated. Okay, so always check the sign of your solution after you get the answer. And then we start to talk about ambiguity of defining magnetic flux, right? Magnetic flux is just B dot S, but like if we have like multiple turns on the same area, then you have to multiply N here, right? Of course, so that your total flux should be not just BS, but BS multiplied by N, the number of turns, right? So that has to be counted. And then we introduce this inductance, the concept of inductance. Inductance is how much of a magnetic flux is going to be generated for a given current. Okay, so magnetic flux and current is always linearly proportional. So if you normalize your magnetic flux by using current, you get a inductance, which is only depends on the geometry of the system. Okay, it does not depend on any other thing. So once you have your system has a fixed geometry, then it basically have a fixed inductance. And self-inductance is about like, you know, magnetic flux due to the current of the same circuit. And then mutual inductance is that the current of one circuit creates a magnetic field, and that magnetic field changes the magnetic flux through the other circuit. So this, in this case, you take into account the mutual inductance. And then mutual inductance we usually note as M21, right? Or M12. Like, and then again, 2 is the source. No, 1 is the source, I think. 1 is the source, and 2 here is the loop, okay? And then M12 and M21 are basically the same. And then you can actually derive this by using Neumann formula, and which is very convenient. Like the mutual conductance between mutual inductance between two circuits must be the same. So then we started to talk about actually obtaining the inductance in various cases. And then this was the first example. And then obtaining inductance itself is pretty easy, right? So all you need to do is just to assume a current I is flowing inside the circuit. And then you can evaluate the magnetic field, and then multiply circuit area and the number of turns of the circuit, and you get the magnetic flux per unit length, or total magnetic flux. And then by dividing this with your current, you get the self-inductance. And then mutual inductance can be calculated in a very similar way. So you can just assume current I, evaluate magnetic flux, and divide the magnetic flux by current I. So is there any question so far? Like about what we learned last time? Okay. So as always, if you have any question, you can just type in, even though I just you know, move on to other slides. Okay, so self-inductance of toroid. So we're gonna solve the self-inductance exercises, probably a couple more. And then this is one of the representative example of toroid. And here too, the procedure is basically the same. You assume the current I is flowing. And once you assume the current I is flowing, you can evaluate B field. And then B field in this case can be calculated by using Ampere's law, right? By taking your Ampere circuit, like Ampere's loop, like this, right? This is a circular manner. And then if you do, because we've done it already, the magnetic field is actually just written like this in this case. And then magnetic flux through a single turn is that basically if you look at the cross section looks like this, right? And then singleton, this is a single turn. And then if you want to calculate the flux through singleton, you have to integrate B field in this area, and your B field depends on rho. You need to take an integration actually, and then if you actually take the integration from rho equals A to rho equals B, and you get this, and this is your magnetic flux through singleton, right? And then you actually have many turns, And the total number of turns is actually n, right? Because we assign this number n here. So you need to multiply n to the magnetic flux through a single turn, and that gives you the total magnetic flux. Now you divide this by I, you get the self-inductance. Mu 0 n squared h divided by 2 pi log b over a. And then one thing you should notice here is that magnetic inductance is actually proportional to the square of n. Okay, so if you have many turns, when as n increases, the self-inductance, even though, so if as n increases, your B field linearly increases, right? B is proportional to n just. But self-inductance increases quadratically, so it's proportional to n squared. So it increases much rapidly compared to just the B field. So self-inductance, in order to increase the inductance, you need multi-turn loops. Okay, so I guess so far everything is pretty straightforward. But if it's not, you can always leave a question in a chat box. And another exercise is this. By the way, this exercise is about a pair of wires. And then what it says is you have a wire here and a wire there. And then these wires are parallel and infinitely long. And then of course, in the end, it is connected somehow, right? So in this case, what's the self-inductance per unit length of wire? Okay, and here we assume the radius of wire is a. Okay, it's non-zero, and the distance between center to center distance between the wire is d. And then here we ignore the flux passing through the wire themselves. So you know that magnetic field is gonna be like this, right? And then here, due to this thing, magnetic field is gonna be like this. So in between the wires, magnetic field is gonna be along y direction. We know that. And then here, and here also inside the wire, there should be some magnetic field. But what we are saying is that we are going to ignore the amount of magnetic field, magnetic flux inside the wire. And then if you think about this problem, this actually tells you about the ambiguity of a circuit area. Because in this case, your circuit, your current is not a line current actually. It's actually a volume current because A is non-zero. Right? So there's an ambiguity here. There's an ambiguity of choosing area. But the problems tells you that ignore the flux passing through the wire themselves. You can just set the area of the circuit just in between the wires. Okay, so that's one convenience. And by the way, this problem has been appeared many times in our KAIST EE graduate school entrance exam. So nowadays we don't have any entrance exam, right? But like just 3 or 4 years ago, there exists entrance exam and KAIST EE graduate school, and then this problem was like appears very frequently, like almost all the time. So asking people about the concept of the self-inductance. And then solving this problem itself is easy, right? It's just, the magnetic field. In order to obtain the magnetic field, we know the magnetic field due to a line current. So this part is due to the current 1. And then this part is due to the current 2, right? The magnetic field. And then you need to add them up here. So magnetic flux per unit length, you can easily calculate because you already have a B field. You have a B field, and then so you plug your B field in, and then you take dx. So dx is along this direction, and then integrate it. Because it asks you about magnetic flux per unit length. Length is already divided out, so you don't need to worry about L, and only integrate from dx. And then here the integration should run from A to D minus A. And this is obvious, right? Because we decided to ignore the flux inside the wire. So integration begins at A and then ends at D minus A. Right? So if you actually do the calculation, you get this: mu 0 I divided by pi log D minus A over A. And now you see why we assign non-zero A, right? If A was 0 in this problem, this term diverges, right? This term diverges. So your self-inductance diverges, which is not physical. So in order to prevent this type of thing happens, we just assume that like non-zero A, so that the problem is tractable. And then self-inductance per unit length is easy. Just, once you get the magnetic flux, then that's it. Just divide it by I, and that's your solution, self-inductance. So this is actually the last problem of obtaining self-inductance. Is there any question before we move on to an exercise of solving mutual inductance? So it's not too complicated, right? It's once you are able to B field, that is pretty much it. Once you get the B field, then all you need to do is just take an integration, P dot dA or B dot ds, and then obtain magnetic flux, and that's it, right? And similar thing applies to mutual inductance. There's nothing difficult here. So let's move on to the mutual inductance, because you are solving two easy problems so far. So I just want to bring, well, this one is also easy, but anyway, things requires more thinking here. So the problem is this: you have two circular loops. Circular loop 1 at the origin, circular loop 2 at z equals h, and then these two loops, both of the loop lies on the same sort of a, they are parallel, basically, parallel to the xy plane. Okay, and here's an interesting condition. H and B, both B and H, are much larger than A. A is the radius of a smaller circuit. Okay, so B and H are much larger than A. In this case, we want to evaluate the mutual inductance, so M12, which is equal to M21. So it doesn't matter which way you calculate it. So how to calculate this? So let's say if you want to calculate M12, means you want to evaluate the magnetic flux through loop 1 due to current 2, right? So if you want to evaluate this, you want to let this circuit having current flow and evaluate magnetic flux in loop 1. So that's how you evaluate M12. And when you want to evaluate M21, you let this circuit have current I and then evaluate magnetic flux through loop 2. Then you can get M21. But we already know the solution must be the same, right? And in this case, which one should you calculate? Which one should be easier to calculate with this condition, with this approximation available. M12 or M21? Can you answer? Can you type in like which one would be easier to calculate? M12. Yeah, many of you got the correct answer. Yes, yes. M12 should be easy, right? Because M12, all you need to do is to evaluate magnetic flux through loop 1. And the loop 1 area is tiny. So what we can do here is we can do a very convenient thing. When we evaluate psi 1 due to current 2, what we need to do is we can just evaluate magnetic field at the origin. Let's say that as a B0 at the origin, and then dot product, and then do the multiply just 2 pi, pi a squared, the area. So what we do here is that instead of actually taking integration, because A is very small, we can just assume, we just ignore the variation of the B field within the circuit area, but just multiply pi a squared. This is approximation that makes your life much, much easier. And then B field calculation is also doable because you have a loop here, and then you can easily evaluate the magnetic field at this position due to this loop by using Biot-Savart law. Okay, so if you do it, B12 is this, right? I don't want to go through actually how to obtain the B field because we've done it already. You can, all you need to do is using Biot-Savart law. And then psi 12 is B12 Z component multiplied by pi a squared. And then you can get this answer. So by dividing this with I2, then you get this. This is your mutual conductance, mutual inductance. Very easy, right? Very, very easy. Now, then is it really impossible to calculate M21? M21, you think it's much more complicated because you have current carrying loop, and then it's gonna create B field like this, right? Because it's very, very small. It's like a dipole. You have a dipole here, small dipole here. And then that creates B field in this manner. And then in this case, of course, you have to carefully calculate you cannot ignore basically the variation of the B field within the circuit, right? But at least you can approximate this as a dipole. There's no problem doing that, right? Because A is much, much smaller than H or B. That's the condition for having dipole approximation. So if you do it, this is the second solution. So fortunately, we know the vector potential of the dipole. So dipole, if you have a dipole in the origin, at the origin, we know the vector potential like this. Okay. And then how we obtain this? Well, I'm not gonna tell about it now because we've done it already when we learn about magnetic dipole moments. So just go back and take a look at that lecture notes. So assuming that we have dipole like dipolar vector potential, then and then think about this integration B21. So B field here, and then take integration S2. And because B21 is curl of A21, and by using Stokes theorem, you can make this into a line integration, right? So A dot dl, and A is given, right? And so, and then dl is given. So in this case, you can easily evaluate, psi 2-1, and you get to the same conclusion. Okay, so M12 and M21 are same. So, well, arithmetically, this calculation is also not too difficult, but this requires you to memorize the magnetic vector potential form, right, of a magnetic dipole, which is not usual thing. So I would say this is much more difficult compared to the first solution. But anyway, either way, you can get the solution, of course. So do we have any question so far? Okay, so if we have no question, we'll move on to magnetic energy. And then after we briefly talk about magnetic energy, we'll move on to the interesting topic of exceptions to Flux rule, as I said earlier. So let's quickly go through the magnetic energy first. So what is the magnetic energy? You can just think about, here I stated that energy is required to start a current flowing in a circuit in order to overcome the induced EMF. So what does that mean is that you can think about situation, you have a coil here, and then you want to run a current through this. But as I said earlier, by Lenz's law, if you start to run a current, then this current create magnetic flux, right? And then, as I said, nature hates change. So this wants to create magnetic flux in opposite direction through magnetic induction. And because of this tendency, it is actually takes some work in order to run some current through a circuit. Okay, so this is what I mean by this. Like, energy is required to start current flowing in a circuit in order to overcome the induced EMF, because the induced EMF wants to suppress the running of the current. You have to overcome it, and in order to do that, you need some energy. Okay, and then of course, once you form a current, then if you just turn off the current, then same thing applies. Even though you want to turn off the current, it's not going to be immediately turned off, because you have already formed magnetic flux, and then it doesn't want to go away instantly, right? It's just and this way you can basically extract the energy out. And in a sense, this process is similar to electric conductor, capacitor. So once you charge up the capacitor, of course, in order to charge up the capacitor, you need to do some work, right? But once the capacitor is charged up, then you can use this as your energy source. You can, you can like put some electric bulb here, then it's gonna be light up due to this capacitor, and then charges are just moving in the original position. Same thing here. In this case, what you are building up is current, not charge. Okay, in order to build up the current, you need to spend some energy, but you can of course take this energy out when the current is off. Okay, and then how much energy you can actually easily calculate, because you know that the power is V multiplied by I. We know this, right? So by taking the time integration of this power, you get the energy. And then EMF, electromotive force, is negative of d psi dt, and then dt cancel out. It becomes I d psi. And then again, psi, like in this case, if you have just a single loop, psi is just Li, right? Because definition of L is psi divided by I. So, and then as I said, L doesn't change as a function of time or current. So L stays there, and then d psi is just the L di. Okay, and you have another I in front. So if you want to charge up, it's not charging up, like run a current from 0 to I, you get 1/2 Li squared. This is your magnetic energy in a inductor. Okay, so if you have an inductor with in self-inductance L, your magnetic energy becomes 1/2 Li squared. And then what happens if we have multiple loops? Well, in this case, you need to carefully think about like what's gonna happen. But here, the first loop, when you run a current through a first loop, it's just a regular 1/2 Li squared. But if you want to run a second loop, run a current I2 in the second loop, it's not simply having current in just the first loop, right? Because you also take into account the mutual conductance. I'm sorry, mutual inductance. So the total energy actually is sum of self-inductance term plus the mutual inductance term. So the total energy is given by this. And here, the mutual inductance, the energy associated with mutual inductance can be positive or negative, depending on the direction of the or orientation of the B field. So when the B field of two loops strengthen each other, then we need to take positive sign. But when the B field of the two loops basically cancels each other out, cancels out the magnetic flux of each other, then you can take minus sign. Okay, so what you need to keep in mind in this case is that the energy, magnetic energies, obtaining magnetic energy not only involves the self-inductance, but also involves the magnetic inductance, the mutual inductance. And then the way mutual inductance work is like, as I said, it's like if the current of the two loop runs in a strengthening direction, then you get positive sign. But if it's a negative direction, then we get minus sign. Okay. And then you can also manipulate this equation a little bit. So we begin with 1/2 Li squared. And then Li squared is I times Li, and then Li is psi. So it's I psi divided by 2. Psi, by definition, is B dot ds. And then B, by definition, is curl of A. Right? And then from here to here, we do Stokes theorem. So surface integral becomes a line integral. Right? And then, of course, we can put I inside. I mean, there's no problem putting I inside the equation. And then, actually, IDL, this is a case of a line current, but more general case is the case of volume current. So we change this to JdV. Okay, so IDL is actually JdV in volume current case. And then J is curl of H. This is Ampere's law. J is curl of H. It's Ampere's law. And then we use a vector relation, divergence of A cross H is H dot curl of A minus A dot curl of H. So we use this relation to divide this into two, divide this term into two. Okay. And the first term, we reduce curl of A back to B. So it's like H dot B, 1F H dot B dV. And the second one, we use divergence theorem. So we change the volume integral to surface integral, like this. And then here we apply the similar argument, right? As R goes to infinity, H is proportional to 1 over R squared, and A is proportional to 1 over R, and then S proportional to R squared. So in total, it should go, it should disappear as R goes to infinity. So if your volume becomes infinitely large, right, the whole space, in this case, we ignore this, the second term. This argument is basically exactly same as what we did in our electrostatic energy calculation. So we ended up having only the volume integration, but now this volume integration becomes the entire space integration, right? And then the energy is equal to 1/2 H dot B. And in this sense, we can define 1/2 H dot B as a magnetic energy density, right? So if you're not having any problem in understanding this, I recommend you to take a look at our lecture notes for electrostatic energy derivation. It's basically the same, exactly same. So in electrical energy derivation, we began with 1/2 CV squared. And then, by using all these derivation formula, we got the correct answer. And then, yeah, so just take that into account. And Kim Junmo asks, when we apply a Stokes theorem to A, why don't we use closed loop integral? Oh, it is closed loop integral. It is. Yeah. So sorry about that. It's closed loop integral. Yes. But yeah, so L forms a closed loop, so just don't need to worry too much. Okay, so do we have any other question? So this derivation is again same as the electrostatic energy, but what's important is the result. Okay, so there are two ways to evaluate magnetic energy. One is doing 1/2 Li squared. And in this case, you need to know what is L in your system, like L, the inductance, self-inductance of your system. If this is difficult, you can evaluate magnetic energy by just integrating 1/2 H dot B. H dot B is much straightforward thing, right? You can evaluate B field everywhere. And then that gives you H field everywhere. So once you know the B field and H field everywhere, all you need to do is to take volume integration for entire volume, right? Then you can get the magnetic energy of a given system. And Kim Kiwan asks, right, so when we say J is equal to curl of H, we kind of assume that J is not a total current, but a free current. And here the same, like just as we argued in our derivation in electrostatics in materials, what we can control is free current, not the total current. So what we are turning on and off is the free current. So that's how we take into account, only the free current contribution here. And then Jung Yeonho asks, how can we ignore A cross H dot ds? Okay, so you probably remember the Biot-Savart law. And then Biot-Savart law says that B is proportional to 1 over R squared, right? And so H is also proportional to 1 over R squared. So when R is very, very far away from the source, H must be proportional to 1 over R squared. And then A is just an integration of H, right? Because curl of A is B. So the relation between these two is just the integration. So you have one dimension added. So A should proportional to 1 over R instead of 1 over R squared. And then S, by definition, is proportional to R squared, right? So if you multiply all this everything still proportional to 1 over R, right? So as we take our surface very, very far away from the current source, then you can ignore this surface integration because it's, in total, it is proportional to 1 over R, right? So that's the logic here. I hope that answers your question, Jung-Yeon. Okay. So do we have any other question here? Okay. Then let's compare these two systems. As I said, it is very instructive to compare everything in electricity and magnetism. So in electrostatic energy, electric energy can be stored in capacitors, as we said, right? And here we store charges at each conducting plate, right? And the charge amount is basically CEV, written as a CEV, capacitance times voltage applied between the plates. And the energy here, in this case, the energy is 1/2 CEV squared, right? And then this can be also written as this. So V times rho F. So V times rho F dV is like a potential times charge distribution and dV. And here rho F, again, because we are dealing with free charges. And this is equal to 1/2 dE volume integral, right? This is just like electric energy density. And here, in magnetic case, we have a solenoid, like loop. And then in this case, we run current through it. And then what we basically store is magnetic flux. Okay, so we build up magnetic flux by running a current. And in this case, we build up charges by applying the voltage. So we do this. And then the magnetic energy is 1/2 Li squared, just like it's like 1/2 CV squared. Okay, and it can be also written as a 1/2 H dot B integration or A dot JF dV. So A is the magnetic vector potential. JF is the current density, free current density. Looks pretty similar. V here is the electric potential, and then rho F is the free charge density. And then so you can see the correspondence. So they are pretty similar to each other. Although they're different phenomena, but like, you know, at least if you look at these two things, it would be beneficial for you to understand what's going on in terms of magnetic energy. Okay. So again, what you are storing here is charges. And how to store charges? By applying voltage. Here, what you are storing is magnetic flux. How to store it? By applying current. Right? So that's how it's going to work. And then the stored magnetic flux actually has energy. And here, stored charges has energy. Okay, so this is basically a brief explanation about the magnetic energy. Do we have any question? If not, I'd like to move on to the interesting part of exceptions to the float rule. Okay, so let's talk about this. So here, this problem, you will encounter a very confusing situation. So if you look at this, the problem is like this. You have a magnetic field along z direction, and then you have a bar here, axis, and you have a here solid disk, metallic disk, rotating with angular velocity omega. And then here everything is conducting. Okay, everything is conducting. And then you connect this thing here, 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 and here. Connected. So this is the situation. The current is flowing like this. This is the current flowing direction. So the question is, if we measure the voltage, electromotive force in this case, do we have any force? Do we have any electromotive? Do we measure any voltage? Well, if you want to know this, the answer to this question, you have to obtain psi, right? It's a magnetic flux. In order to get the magnetic flux, you need to do B dot ds. B is evident. B is just given as a constant z-directional field. And then if you think about this part of the circuit, it's orienting, perpendicular to z direction, right? So this part of the circuit actually doesn't help in terms of magnetic flux. And even though it helps, it doesn't change as a function of time. So in order to get the electromotive force, you need the non-zero d psi dt. But in this case, what is changing as a function of time? It's difficult to know, right? And in this case, what is more confusing is that from here to here, current can go anywhere. So like, current never goes like in this manner. It can go this way, this way, this way, this way, like in a very diverse way. So in this case, it is very difficult to determine what is your circuit area, right? It's difficult. So how would you solve this problem? Well, obviously you cannot solve based on what you learned so far, right? So one way to deal with this problem is to going back to the basics. So thinking about the microscopic force. So the speed of a point on the disk at rho. So it's when, if this is rho, then the speed of the point, this point on the disk, is omega rho a phi, right? That's what we know. Because angular velocity is given, each point on disk has a velocity like this along phi direction. And so magnetic force per unit length. So because charges are also moving with this angular velocity, so you can evaluate Lorentz force. So magnetic force is U cross B, right? Per unit charge. So it's U cross B. And you know U and you know B, and you can calculate magnetic force. And then magnetic force is along rho direction. And then amount is omega rho B0. Okay, so this is a microscopic force that applies to your charges at each position of a disk. And because your connection is made here and there, you need to evaluate evaluate electromotive force by integrating your microscopic force along the line, right? If you do that, or it doesn't matter like what path you choose. I mean, because there is a dot product anyway, what you're gonna get is just omega a squared B0 divided by 2. That's the integration rate. Okay, so from this you can know the electromotive force. Okay, here keep in mind that you did not use any flux rule, right? And then we don't know how to use the flux rule in this case because it's circuit is not well defined. So as an alternative approach, we focus on the fundamentals, and then we decided to evaluate the magnetic force, microscopic magnetic force, and then integrate them along the path, and then you can calculate the electromotive force. Okay, so yeah, so this is how you evaluate the electromotive force in this case. And then of course researchers at that time was very confused about this. I mean, if you actually do an experiment, you can actually get the electromotive force exactly same as this if you actually do an experiment. So people got confused, like, okay, I understand that microscopic force can explain this, but what's wrong about the flux rule? Is there any way that we can make flux rule like kind of updated version so that it can be still applicable for this system? And then what people figured out was this. They want to redefine the flux rule in this way. So another approach is to define the notion, the rate of change of flux linkage. So they define flux linkage. It's like an extension of magnetic flux. So in most cases, this flux linkage and magnetic flux are basically the same thing. Okay, just B dot ds and then lambda are same. But like here in this case, because we cannot define S, right? It's difficult to obtain psi. But there's one way to define this. So if you think about this system, like let's say time t equals 0, let's say your circuit was like this. Just making a imaginary line here. Although the current is not flowing this line, but we can just think about a line, like imaginary line here. And then when t is t0, like sometime after, now this line went to this point, right? Because after some time t, this line just rotated and arrives here. And then we can just say that, okay, and after this time, our circuit looks like this. And originally, our circuit looks like this. So this is how we define our circuit area. Okay. Then what it tells is that it actually have time-dependent increase in magnetic flux, right? Because you have like extra area obtained here. So in this case, you basically define the flux linkage as using the area swept by hypothetical line across the disk, and then like basically this area is what this statement explains. Okay, explaining again, even though we do not know how the current is actually flowing, but we just assume a hypothetical line here at time t equals 0. And then this hypothetical line becomes at this position when time t equals t naught, like non-zero. So we use this as our circuit area at time t equals 0. And then we use this as our circuit area at time t equals t. And then we know that this amount of area has been added, right, for the magnetic flux calculation. And then that is how you define magnetic flux. And if you do that, you get the same answer. Okay, so this sounds not completely unreasonable, right? But at the same time, it's kind of a bit arbitrary just to, drawing on hypothetical line and then cut through magnetic field thing. So I personally don't like this type of an argument, like this type of a definition, because I still think this is a bit ambiguous. But anyway, this has some point, right? It's kind of makes some sense. So, I would say it's reasonable, but in my opinion, it's better to stick to this argument. I mean, I would buy this argument instead of this. Okay, so is there any question regarding this? This is interesting, right? This is to me at least, this is a pretty interesting thing, because B.ds sounds very trivial. Like once you get B field, you can just multiply S, you get psi, and then so on and so on, so easy. But like here, if you cannot define your circuit area clearly, then you are in trouble, and that is actually a much interesting problem for me. So Park Seung's question is that, like, can we assume that the length of the line can be increased indefinitely? No, it's not the case. It's actually the lengths of the lines are fixed, and then we are just making a contact here, and then just this entire disk is just rotating. This is the situation. So, we are not actually making here and this position of the disk are not just attached. Okay, we are just making a contact here, but it's not attached. So this one stays there, and then your disk keeps rotating. So I will say this is a pretty interesting problem. And then let me introduce another interesting case, which I think I should go detail tomorrow, next week. But anyway, I'd like to introduce first. So it's this case. So in this case, we have coaxial cable. So it's a cylindrical thing, and then outer cylinder has 0 thickness, and current I is flowing here, and then inner cylinder, which has a radius A, and then it's not a cylindrical shell, it's just a solid cylinder, and having current I. And then here we assume that current is uniformly distributed. So in this case, J is I divided by pi A squared, right? And in this case, what would be the self-inductance per unit length? So let's first think about the magnetic field. Magnetic field is that because current is flowing up, so let's say flowing up here, and then flowing down in the center. So if it's flowing that so inside you have magnetic field along this direction, right? So it's rotating magnetic field you have. And then because current is flowing up here and down there, you can think about a circuit area of like something like this, right? Very far away, there should be connected. These two should be connected. So it's like this. The problem is here you have this part is fine. This part you have like a well-defined path, but here your current is flowing in volume. So you cannot define your circuit area in a definite manner, right? There is again, ambiguity here. How to define your circuit area, so that you have problem in calculating your flux, magnetic flux, right? So the question is asking you how to evaluate the self-inductance. But in any case, you need to first calculate the B field, right? B field is anyway needed. So you have a current, so you can calculate B field by using Ampere's law. And it's very easy. Inside the inner conductor, it's linearly proportional to rho. And then outside the inner conductor, like between A and B, it's like just like a magnetic field due to a line current. And then outside, it's 0 because enclosed current becomes 0. Okay, so this is your magnetic field amount. And we exactly know this. Then what? Is there any good way to evaluate your self-inductance? Because it's difficult to obtain magnetic flux in this case. So even though you know B, psi is difficult to evaluate. But how would you evaluate L in that case? And here again, one circumvent way, one like alternative way of obtaining L is beginning from magnetic energy. So like, you know, magnetic energy is 1/2 Li squared, right? It's 1/2 Li squared. And then another definition of magnetic energy is integration of 1/2 B dot H, magnetic energy density. And because we know B and H everywhere, we can easily calculate magnetic energy without any uncertainty. So we can evaluate magnetic energy by integrating 1F B.H. Okay, that's easy. So once we get the magnetic energy, all we need to do is equate this magnetic energy with 1/2 Li squared, because magnetic energy is also same as 1/2 Li squared. And by using that technique, you can get L, right? You don't need to, again here, you don't need to worry about magnetic flux. We just use some different method. Like we use a magnetic energy can be defined in either way, and then we use it to evaluate magnetic inductance. Okay, so I prefer this way, but next time what we are gonna learn is that how to approach this same problem using magnetic flux. How can we apply the magnetic flux rule in this problem to obtain the same answer? Okay, so yes. So it's already 2:06. I would like to stop here.